Thank you for the introduction, and thank you obviously for the invitation and for all the nice things you do to all participants, and including myself. I would like also to thank Professor Johnson to make a nice introduction, an in-time introduction to my topic, and of course every one of you being there. So following the advice of Geoffrey Beck, I will be talking about something that I don't fully understand. And it's an ongoing work with Raoul Amchek, which you have certainly talked to already with, and Arnaud Durand, who's sorry he cannot join. And okay, we have to say we're stuck at some point, and any help would be greatly appreciated. So it's about 3 scale singular limits applied to oceanography. And okay, there will be a first section about the motivation of the kind of problem we're looking at. Then the second section is about 2 scale singular limits, which is much more understood. And I will recall basic knowledge dating back from the 80s, actually, on the mathematical analysis of these 2 scale singular limits, before moving to the real subject, which is 3 scale singular limits. Okay, so as a motivation, I would like to introduce you to the Tolosa team. And the Tolosa team, they are developing a numerical code which is used by Météo France to make water height previsions near the French coast. Okay, so there is Rémi Baraille, who is the chef, and Fred Couder, who is the main coder, Jean-Paul Villa, Pascal Noble, Arnaud Durand, Sergei Tchatchenko, Victor Michel Dansac, Martin Parisot, Maya Clavaldani, Gaël Richard, and Audrey Pasquet. On the website, which is tolosaproject.com, they have this video as a shower of what they can do. So you can see with the colors. So it's a numerical simulation, which for more than 1 week, I think. So you can see the tides. And you have different scales. We will zoom in to Saint-Malo eventually. Of course, it's not the same code, and it's not the same model which is used on the different areas. But what is, to me, extremely impressive is that when you close here, the resolution is a few meters, actually. You can see details of the pier of Saint-Malo. So they're capable of doing this, which is, in my opinion, extremely amazing. And they want to make it even more amazing by taking into account non-hydrostatic effects near the coast. Okay. The reason why you want to take into account non-hydrostatic effects is pretty obvious. So starting from now, it's my numerical simulations. So it's not at all impressive, and it will be in a one-dimensional torus, so a circle, very smooth data, and nothing much appears. Okay, so I should make it full screen. Well, it's not much better. Okay, so you have an initial excess of mass, which propagates to the right and also to the left, but you don't see it. And we compute the exact solution. For me, the exact solution in the waterways equation, which have been showed just 2 hours ago. And that is a free surface Euler equation in the irrotational framework. Okay, you cannot see it because it's behind, basically. In orange, you have the shallow water equation, the one that you get following the notation of Professor Johnson when you set epsilon equals to, say, 1 and delta is equal to 0. Okay. And in green is the model that they want to use, which is the Green-Agdi system, which takes into account the first-order effects of non-hydrostatic pressure contributions. Okay. Obviously, it's kind of clear that you really want to, in this situation at least, to have non-hydrostatic effects. In particular, because the shallow water system produces gradient catastrophes for generic initial data, and which, in fact, are not here mostly in nature. So if your real solution doesn't produce shocks, you certainly don't want to use a model which has shocks, because if it has shocks, you need to use a good discretization, which is not the discretization that I use. It's not a good discretization. All these oscillations should not be there. It's just because I'm a poor numericist. Okay, so this is the gain of using a non-hydrostatic model. And now what is the cost of using a non-hydrostatic model? Of course, it has a cost. So now I will show you the equation. So a bit of notations, sorry, but it's also on the left and right side of your blackboard. So I denote h the height of the water, so the surface of the water, depending on time t and horizontal position x, which for simplicity here is just in dimension 1, but it doesn't make a big difference. U is the layer averaged horizontal velocity. Okay. And there is a parameter which will play a big role, which is the shallowness parameter, which I call it mu, and which is nothing but the square of the delta that we had this morning. Okay, my fluid is subject to a vertical gravity force, and the simplest nonlinear model describing this setting is the shallow water or Saint-Venant model, which we have already seen, which reads like this. The first equation is the equation of conservation of mass. It's an exact equation. And the second equation is the conservation of momentum. And it's an approximate equation. And the precision of the model is expected to be of the order of your shallow water parameter, mu. Okay. The Green-Nagdi model can be constructed as the next order model when you want to keep the first order non-hydrostatic pressure contributions. So you will add this term in green here, which represents, again, the first order of the non-hydrostatic pressure contributions. So in this term, you have this H double dot. So H dot is the material derivative of H, okay, partial TH plus U partial XH. And of course, H double dot is the material derivative of H dot. Okay, so you just have to add this simple looking term. But now if you think at integrating in time this equation, you have to write it as an evolution equation. That is something where you have only one time derivative, right? So you should rewrite this Green-Nagdi system. The way to do it is to, let me move on. So you say that H dot, this is partial TH plus U partial XH, but using the conservation of mass, this should be minus H partial X of U. And then I take the material derivative of minus H partial X of U. Okay, so I differentiate again with time and with the advection term. And what I get after some algebra is this system, which is just a little bit longer, but which has only one time derivative of H here and one time derivative of U here. Okay, so here you see some terms which include up to third order differential operators in space. Okay, and in front of your time derivative here, there is an operator. There is an operator. It's an elliptic operator. So it's okay from a theoretical point of view because it's an elliptic operator. As soon as H is bounded from below by a positive constant, you can invert and is sufficiently regular, let's say Lipschitz. You can invert this operator and you have all the elliptic estimates that you want. And okay, you can do the theory for this system. You can have stability estimates which allow you to rigorously justify the Green-Nagdi system as a model for the full water wave system with the precision mu squared. And it's been done by first by Lee in 2006, then Alvarez Samaniego and Lan, and finally with full details and in the full setting by Fujiwara and Iguchi in 2015. Okay, so far so good, but it's okay analytically to invert this operator, but of course it has a cost. It has a great numerical cost. This operator depends on your unknown, h, so you cannot do LU decomposition and then do it quite efficiently. You need, at each time step, to construct your elliptic operator and to invert it, and this is a cost that people in Tolosa are not willing to do. It's just too costly. That's what I did for my numerical simulation, because I was in a 1D, very easy setting, but in a 2D problem, in a real-life problem, clearly it's out of the question. So you need another strategy. The other strategy is based on another reformulation of the Green-Nagdi system. So what you do is you name things, okay? So this H dot, I want to call it W, because it represents the vertical velocity of the particles of fluids at the surface. And now the material derivative of W multiplied by H, I want to call it P because it represents the first order non-hydrostatic pressure contributions. Okay. And now my system, so the term that I have here, I can write it as H times P. So I can view this system as 3 evolution equations with a pressure term here, which is nothing but the Lagrange multiplier associated with the constraint W, which is equal to minus H partial x of u, which is needed because of the conservation of mass. Okay, so now I have 3 evolution equations and a constraint. Okay, and this leads naturally to a strategy which is well known for people working on the discretization of incompressible flows, with the strategy being relaxing the constraint. In this setting, it's been first proposed by Favry and Gabrieliuk in 2017, and then there are other groups who proposed slightly different models, but with the same strategy. So Escalante, Dumser, and Castro. I'm forgetting some, and I really like the work of Richard, who interprets the relaxation strategy as weak, as taking into account weak compressible effects inside the your fluid domain, and not only as maybe just a strategy to numerically implement your model. Okay, so the strategy again is to replace this identity by an evolution equation for the quantity P. So now P is no longer a Lagrange multiplier. It's something that you will be able to evolve with time. Okay. You put a small parameter here, hoping that when epsilon goes to 0, the solution given by these first 3 equations and this one, the prediction of this model will converge toward the solution of the Green-Nagdi system, which you know exists, in the limit epsilon goes to 0. And I claim it's a singular limit. It's a singular limit because for any epsilon different from 0, your model is a set of balance laws. Okay, so you have only waves, finite speed of propagation. Okay, and when epsilon goes to 0, it's really this dispersive system where you have an infinite speed of propagation. So there is really something singular in this limit. Okay, so that's what they want to do, and that's what we want to analyze. So this is just a little bit of rewriting the equation to put it on a form which will be useful to do theorems, because I have to apologize, I do theorems. And so you rewrite a little bit, and you rescale a little bit your system, and what you obtain is something like this, where you see that you have 2 types of singular contributions. You have the singular contributions in red, which are of scales delta divided by epsilon, where epsilon is the small parameter that you introduce, that you are free to choose, and delta is the square root of mu. I use the same notation as Professor Johnson. And it is a shallowness parameter. It's given by the physics. You cannot choose delta. So these are order 1 operators of size delta divided by epsilon. And then you have this order 0 operator of size 1 over epsilon. Okay. after just a little bit of manipulation, you can rewrite this system as under this following form that we will use. So it's kind of a system of balanced laws, but so you have a S0 partial tu plus S1 partial xu plus delta over epsilon L partial xu is equal to 1 over epsilon ju. And what's important is that S0, so U is my set of unknowns, okay, so here it's 4-dimensional. S0 of U is a matrix, it's 4 by 4, and S0 is symmetric, definite positive. S1 is S1 of U is a 4 by 4 matrix, which is symmetric. And L and J are matrices which are constant coefficient, and it's extremely important. L is symmetric, so that's L times partial x is a skew symmetric operator, and J is skew symmetric. Okay, there are many systems which can be put in this framework or a related framework, stemming already from geophysical equations. Okay, you can have a rotating equation with the equation that you like, so Euler, shallow water, Boussinesq, or others. It appears also in compressible MHD. This kind of system arises naturally in various contexts in geophysics. Okay, so there has been already quite a few works related to this kind of problems, but I think here our scope is a little bit different. First, because all these equations have been analyzed on a case-by-case in case-by-case setting. Okay, so they often rely quite finely on the structure of the equation and dispersive properties of the equation, and we don't want to, so we would like to have a general framework. Secondly, one big difference is that often the mathematical analysis of this kind of systems is really about, often it's a weak convergence. You want to kind of, through weak convergence, get rid of all the small oscillations, and here our scope is a little bit different because and simpler, in fact, because we don't want to have little oscillations in our systems. Okay, this is a numerical strategy to solve the Green-Nagdi system, and we would like to avoid introducing small oscillations. We will be talking about that later on. And finally, most often in this analysis of this kind of systems, people look for what is usually called the distinguished limit, okay, where you will relate the size of delta and epsilon. You will take delta is equal to, say, square root of epsilon, for instance. And we don't really want to do that. We want to really keep our parameter set to be of dimension 2, because again, delta and epsilon have not really the same role. Delta is given to you, you have no choice. Epsilon, you have the choice. So we want to, use these facts and give general information in a wider regime than a specific distinguished limit. That's the hope, at least. Okay, so now let me move on to two-scale singular limits. So I'm forgetting about the other 0 terms, and I'm keeping only, if you want, the conservative terms, which are singular. And now, of course, I have only one small parameter. Okay. The mathematical analysis of this kind of problems started in the 18th by the pioneering works of Kleinerman and Maida, and then there has been quite a lot of activity, Browning and Kreis in 82, Ukai, Chauchet, and many other after this. It's now a quite well understood subject, and there are very nice surveys if you want to dig in the subject. I will be only scratching the surface here. So I really like the Séminaire Bourbaki of Isabelle Gallagher in 2003, which in my opinion is the best way to enter into this subject. But of course, these ones are great too. Okay, the main motivation for this kind of study, I would say, at least that's the first example that you see. It's the weak compressible limit for the Euler equation. Okay, so you start from your compressible Euler equation, okay, which looks awfully similar to the shallow water equation, but that's just okay, by chance somehow. You do a scaling in your argument, okay, so U is small, your density is a small perturbation of a constant density, and you're looking at long time asymptotics, okay. And then what happens is that, at least formally, but in most cases, now it can be really rigorously justified, that the gradient horizontal, so the spatial gradient of your perturbed density will converge at least weakly to 0 as epsilon go to 0. And your velocity field will converge at least weakly to U0 as epsilon to 0, where U0 satisfies the incompressible Euler equation. Okay, in particular, U0 should be divergence-free. And if your initial data is not initially divergence-free, what it means is that there is a boundary layer in time, accounting for the fact that you have rapidly propagating acoustic waves, which in the limits epsilon goes to 0 are infinitely rapid, and hence you don't see them. But I don't want to go into the details of Euler equation, and I want to show you little facts about two-scale singular limits using much simpler toy models, which will be of this form. So my first equation, partial th is equal to 0, is just to give me some function h, which will depend only on space. Okay, and then I have a scalar equation, which is just an advection equation, with the velocity 1 over epsilon times a, where a will be a function depending either on h or on u. And we will see what appears. So you can really see that this toy model really fits into this kind of equations. Okay, so first case, let's assume that my function a depends only is equal to h, so it's here. And so, okay, you have a passive scalar equation, how simple it can get. So you know that your function u will be constant along the characteristic curves, which are given to you by the velocity field 1 over epsilon h. Okay, so depending on space, so the characteristic curves, they do curve quite rapidly because there's a 1 over epsilon, but they will never come close one to each other. And if they don't come close one to each other, then actually everything is fine. So I can show you this animation. The solution U changes shape quite rapidly. If you look at the scale, it's quite rapid. But at each screenshot, if you want, you remain always smooth if you started from a smooth solution. Okay, so that's a good situation. Now let's change our function a here and let it be 1 over 1 plus u, because why not? And what happens is that now your equation here is a nonlinear equation. It's a Hopf equation, okay, with, again, the parameter 1 over epsilon. So you know your Invisit-Burgers equation, and you know that it will generate a gradient catastrophe in finite time, because the characteristic curves are straight lines, but not with the same slope. So at some point, they will cross. And when they cross, it means that your solution becomes multi-valued. So there is a gradient catastrophe. Okay, the animation. Right. So the gradient catastrophe appears, and it appears quite rapidly because of the scaling. It appears at time epsilon. But not really. It depends. It appears at time epsilon divided by minus the infimum of partial xu at time t equals 0. So it means that if you want to have a solution on a time interval of size 1, then you need to assume that partial xu at time t is equals 0 is of order epsilon. And if you look at the equation, it tells you that what you really want to have is that the time derivative of u is initially uniformly bounded. In this case, everything will be well, and you can define a solution on a uniform time interval. Okay? So now how can you prove this kind of results for general systems? So we will follow different strategies which have appeared. There is a standard strategy dating back from the 50s, and then which are not related to singular limits, and then the two pioneering works of Browning and Kreis and Chauchet about these singular limits. So I try to explain this strategy with the diagrams, and I basically failed with Raula, but maybe I will. It will work with you. I don't know, but okay, that's the way I understand these proofs actually. So you want to use the energy method. You want to use the energy method because the structure of your equation leads you to use the energy method. The point is that if you do the L2 inner product of this term with respect to u, it vanishes entirely because L partial x is a skew symmetric operator for the L2 inner product. Okay. So if I test my equations against u, I obtained a differential equation for the L2 norm of u, but depending on other norms. So I want to have a closed differential equation for a functional for an energy functional. Okay. So the standard strategy consists in differentiating my equation with respect to space and then testing it against the space derivatives of my unknown in order to enrich my energy functional with the space derivatives of my unknown. Okay, so I can do this, and this will always vanish because L commutes with the space derivatives. And this will allow me to have a differential inequality for a functional controlling the x derivatives of my unknown. Let's say S x derivative of my unknowns, provided that I have a control of S minus 1 derivatives of the time derivative of my unknown. Okay, partial tu in h s minus 1. And then the standard strategy says, well, but look at this equation. If you control u in subspace hs, so if you control s derivatives of your unknown in the L2 norm, then you can control s minus 1 derivative of the time derivative of u simply by applying the inverse operator of s0 of u, putting everything on the right-hand side, using product estimates in subspaces, and everything is fine. Everything is fine when you do not have this 1 over epsilon parameter, because if you have this 1 over epsilon parameter, well, it costs you a 1 over epsilon, and it will work only on a time scale of size epsilon. So the standard strategy will work only if epsilon is non-small. So it doesn't work in our framework. The idea of Browning and Kreis is not to use the equation to control dtu, okay, but to continue to use energy estimates to control dtu. Okay, so you will differentiate your equation with time and space, and you will test this with the differentiation of your unknown with time and space. Okay, so you have an energy functional which will control this, provided that you control this. And for this, you use energy inequalities and this until you reach to an end, and eventually you have a closed differential equation for a functional which controls everything here. So that works perfectly fine, but now you realize that your energy functional is quite restrictive. And okay, it propagates, but it propagates if initially your initial data for at time t equals 0, and this energy functional is of size 1. And this puts quite a strong restriction on the initial data. You want to enforce that all s time derivatives of your initial data are of size 1, which is not at all obvious when you look at your equation. Okay. So then, a few days later, arrived Chauchet with very clever ideas. It's one of my favorite proofs. Okay, so what he does, always the same things at the first level. Okay, nothing changed. And then he realized that for only time derivatives of your unknown, you have a scaling which works quite well and which makes it possible to only have assume that the first time derivative is of order 1, and then you can allow your second time derivative to be of size 1 over epsilon, and then 1 over epsilon squared, and then 1 over epsilon cube, which puts no further restriction actually on this, because the control of this with this scale is given to you by the equation. So it works for pure time derivatives, but it does not work for time and space derivative. For time and space derivatives, you need to do another thing, and you need to use the equation. And here it's okay, a little bit technical, but interesting as well. You need to decompose your unknown set as slow modes and fast modes. The slow modes are defined by being in the kernel of this operator L, and the fast modes are defined as the ones which are defined in the orthogonal space, which is the image of L. If you're in the kernel of L, then this term vanishes, and you can trade one time derivative for one space derivative without losing this 1 over epsilon. If you're in the image of L, in fact, you will do the opposite. You will trade a space derivative for a time derivative with a gain of a factor epsilon. So in the first case, you can what you do is that you can move in this direction, so you control this with respect to this. And in the second case, you will be able to control this as a function of this. And then you can combine everything, and eventually you can interpolate everything here with this. I see some smiles, and I'm very happy because it's really a nice proof. Quite clever idea. And quite clever idea, and eventually it gives you the result that you want, which is that you only need to prepare one time derivative, and then you have a strong convergence, a strong control of your energy functional on a time interval of size 1. Okay, so it's so beautiful. We want to do it for our two-scale systems, and unfortunately, it won't work as well as we want. Okay, I want to show you a little bit what is the deal with the two scales and what are the possible issues. So now we have these two problems. We have an order 1 term which is of size delta over epsilon now, and we have an order 0 which is of size 1 over epsilon. And remember that delta is small. But delta cannot be too small. Because if you take delta is equal to 0, this term vanishes already, okay? And so what you have here, okay, so you on this toy model, what you have is an oscillation with velocity 1 over epsilon h, with a function h which depends on space. Okay, so it's rapidly oscillating and not at the same speed at for every point. Okay, so I think you can guess what will happen. The fact that you're oscillating, so I'm plotting on the real part here. The fact that you're oscillating at different speed will generate small scales very rapidly. And obviously, it's extremely bad if you put it in a nonlinear model. Now everything blows up extremely rapidly. Okay, so you cannot take delta is equal to 0. The limit delta small is dangerous. Now I have another simulation where I have both terms. Delta is non-zero, but it's still small, and this is what happens. Okay, so it's a little bit crazy, but not as bad as previously. And what you can sort of see is that there is a small scale which is generated. My initial data is basically of this size, and then there is oscillations with this size, and this size I claim is of order delta. So it's small, but it's not. It does not go to 0 when epsilon goes to 0, and that's the point. Okay, so that's the kind of feature that we want to reproduce in our theorems. So here is a result that I had in 2019, and which scratches the surface of this kind of phenomenon. So I was able to prove that there is an energy functional which propagates in time over the good time interval. And this energy functional is, okay, you have a free parameter m between 1 and s. S is the number of somehow the space derivative that you want to control, okay, uniformly. And m should be greater than 1 and less than s. So for the first mj derivative, I want to control uniformly these time derivatives, okay. And then starting from m plus 1, I have this weight which allows my time derivative to be large. And I want to allow this because this allows me not to prepare the initial data. Okay. But in fact, I still need to prepare the initial data. If that was 1 over epsilon, I would be very happy because I could say, okay, this is trash actually because I can control this with respect to this by using the equation. So I could forget about this. But no, I can't because I have this small delta parameter here. Okay, and in fact, if I try to use the equation to control this as a function of this, I have a loss, and this loss is of size delta to the power m minus s. Okay? So this is a positive and a negative result. It tells you that okay, you can have a well-posedness argument, you can have a control of your own energy, but there is a clear warning here. There is there is this delta, and it means that you need, in fact, some level of preparation for all time derivatives up to the order s. So it's quite stringent on the preparation of your initial data. Okay, the proof is just a combination of Browning for as long as you want to be uniform, Browning and Kreis. And then when you don't want to be uniform, you use the proof of Cauchy, but then you realize that you adapt the proof of Cauchy and you realize that there is this bad delta appearing here, and that basically there's okay. You need new ideas if you want to have a better result. Okay, one comment here, which is maybe important. In our situation, you have two kinds of variables, of unknowns. There is h and u, which are given you by the physics, and there's w and p, which is somehow a free parameter, this is what you have at hand, and you're free to choose. Okay, and so there was a second part in this paper showing that for any sufficiently regular h and u that you give myself, I claim that it is possible to prepare the initial data for p and w so that this will be of order 1. So this is positive, but the bad thing is that the formula, if you want to prepare the initial data, are quickly cumbersome, and they will be not used in real-life application. So this result was fairly well received by the community, and they quickly, in the next papers, said, well, this is my strategy, and in this situation, it has been proved that it works. But I was very frustrated by that, because they only kept the positive result and never mentioned the negative result. I'm not showing that it works perfectly well. I'm actually pinpointing possible issues and the fact that you need to prepare very well the initial data, which they never do. And so I was angry by myself and ruminating, and it took me a lot of time to realize that I was the silly one, and that they're doing numerical simulations and it works perfectly fine for them. So it's my error that this theorem is clearly not sharp enough to reproduce what's happening for real. So that's basically what we want to do with Raoula and Arnaud. I want to show you a numerical simulation. Okay. So this is what happens when you do not prepare the initial data. When actually you do a quite silly choice of initial data for W and P. And you see, so the orange line is the relaxed one. So it has these little oscillations, but you see it's not too bad, actually. It does not blow up in your face, actually. Okay, now if you really zoom in into the differences, you can still see that there is a problem if you don't prepare your initial data, because I take several values of epsilon, I'm plotting the difference between the limit system and the RAG system, and that does not appear it does not appear to be converging with epsilon if you do not prepare the initial data. The error is small, but of a certain size, which is certainly bad. But if you prepare just sufficiently well the initial data, then apparently you obtain indeed convergence as epsilon goes to 0. And this is I call mildly well prepared data, in the sense that it is not as prepared as in the theorem that I showed to you. It's much less prepared. So what we want to do again with Arnaud and Raula is, well, first we plan to extend the analysis to more realistic situations, in particular bottom topography. Raula had a very nice idea, so it's checked. Good. And then we want to analyze the error for not so well prepared initial data, and this is not checked at all. And okay. And the aim for this is to we hope to be able to provide a really helpful information for people who make operational decisions in their codes. To in particular, they need to understand if it's important to prepare the initial data, and how small epsilon should be if you want to secure a certain amount of precision. And well, our aim is to help them to make this kind of decision. Okay. So we're not completely stuck. We have one idea that I want to show to you, and I want to show to you why it's better, but it's not perfect. So okay. So this is the results that I showed to you with the diagram. Okay. So you can control an energy estimate where your initial data or your data is uniformly bounded. The first time derivative of your data is also uniformly bounded. And then each time you differentiate more, it can be of the size delta over epsilon, then delta squared over epsilon squared, delta over epsilon cube. Okay. This is the state so far. The next idea was to add additional weights. So in blue, you have the weight with respect to the number of time derivatives that you're looking at, and in orange, it's the number weight according to the number of space plus time derivatives of the quantity you're looking at. And you should do the product of the blue and orange. Okay. So for low space plus time derivatives, you do nothing. You want to be of order 1 because you still want to have a uniform control. You still need to have a uniform control of these guys in order for the energy estimates to work. But then up to some point, which can be at least greater than d over 2 plus 1, you can start to put big weights as you move to the right. Okay, so you can multiply here by delta minus 1, and you can multiply here by delta minus 1, and so on and so forth. Okay, and the advantage of this is that when you look at everything, you realize that everything above this line can be forgotten, because the control of everything which is above this line is given to you actually by the equation, and the scales are quite correct. Okay. So it means that in terms of preparation of the initial data, instead of preparing all the big triangle, in fact, you need to prepare only up to here. So only up to S0 time derivative, where S0 is something that you give yourself greater than d over 2 plus 1. So this is again, and I like the fact that somehow the small scale delta is visible here. Up to, starting from some point, you pay a price of delta minus 1 because there is a small structure which has appeared, even if it was not there initially. Okay, so it's better. But it's not perfect, and I want to show you the result of a numerical simulation. It's my last slide, which shows you that the picture that the previous slide was not perfect. So we start with an initial data, with a flat surface, okay, and a sinusoidal velocity, which pushes the water in the middle. Okay, so this is the solution that you get with different values of epsilon, and they are superimposed. You cannot see anything. If you want to see something, an option is to differentiate your solution for the surface deformation. So I differentiate 4 times on the left, and here we start indeed to see the difference. And if you look closely, we start to see some wiggles here, which is the scale generated of size delta. Okay. And if I want to see it even more, I will continue to differentiate this thing. And if I go up to the 8th derivative of the surface deformation, then the small scale contribution becomes dominant, and you can clearly see it. And what I wanted to show you here is that the maximal amplitude of these small scale contributions appears in an intermediate regime value for epsilon. So first, as epsilon decreases, the amplitude of your small scale becomes bigger. And then after a threshold, which appears to be delta squared, then it starts to decay and to tame, or I don't know how to say it. And okay, it becomes smaller and smaller as epsilon is smaller and smaller. This last bit is maybe not completely surprising, because you want to have a convergence towards a limit solution which does not generate these scales. So somehow this is consistent with this, but I would like to be able to explain it just looking at my relaxed system and not really using some knowledge of my limit system. And I would like really to be able to characterize somehow what is this threshold, really the fine behavior depending on delta and epsilon of everything. So clearly we have not understood everything. So if you see Roland and myself arguing on a table, it's probably about this, and you're welcome to join. Thank you for your attention. Which one?
When you say the school scientific part, you say that you see very slow modes and fast modes. With respect to epsilon, slow and fast?
Yeah, that's you can think fast as acoustic waves and slow mode at the incompressible flow. And so there's one which propagates at velocity 1 over epsilon, and the ones which basically do not propagate. Yes, you can see this like this. You can see indeed, so okay, if I had only this triangle, I could propagate this, and then I'm trying to have this this kind of propagation of regularity, which does not come for free in this setting, and you have to figure out exactly what is the size of the objects if you want to propagate them. But it's exactly this here. Mm-hmm.
I have my numerical background, so what numerical method would you use for simulation? Because in a way, taking either highlights.
Yes, it's a spectral method. So okay, I cannot make more than 8 derivative. You can see here it starts to be really so a rounding error precision, but I think it's reliable. Yes. No. Yes. Yeah, I think I mean, in the relaxation method, there is a dissipative relaxation and there's conservative relaxation. So people in this business, they like conservative relaxation because, okay, conservative. You start from a conservative equation. You don't see why you should add dissipation somehow. But somehow I'm expecting that from a numerical point of view, it could be useful just to, in fact, add just a little bit of dissipation, and probably all the small scale will be killed by. Okay, will be killed simply by this, but okay, that would feel like cheating somehow a little bit. No, it was all conservative equations. There was an elliptic operator, but it was really in a conservative framework. So it's all Hamiltonian and yes. Okay, I don't know, but I'm sure that if I do this and I talk with Sergei Gavrilyuk, he will be extremely unhappy. Mm-hmm. It's conservative, it preserves an energy, and the one of Favry and Gavrilyuk preserves the Hamiltonian structure. Mm-hmm. The only physical interpretation I can get is from the work of Gaël Richard, who interprets it as a weak compressible effect. So it can be done, but he's saying that okay, he had to discard terms which in fact would be higher order than what you keep eventually. So it's not really a rigorous derivation, but somehow still as a matter of interpretation, you can think of it as so the propagation, the speed of propagation 1 over epsilon would be the propagation of acoustic waves. Yes. Yeah. Everything could be done in 2D. I chose the 1D because its formula are slightly simpler, but everything can be done in 2D. No difference. Mm-hmm. Yeah. To preserve the energy. Or otherwise, no. Yeah. Okay. Thank you.